Hello everyone. As Jay mentioned, the story that I'm going to share with you all today is about my work on enhancing the hydrophobicity of catalyst. The way a catalyst works is pretty analogous to how the spinach used to work for Popeye the Sailor Man. Remember how he used to eat a can of spinach that would give him tremendous amounts of energy, allowing him to do a lot more work than he usually could. Similarly, when you add a catalyst to a chemical process, it not only increases the rate of the reaction, but it also reduces the energy requirements, making the process more efficient and sustainable. The class of catalysts that I am working with are called zeolites. These are three-dimensional microporous materials with different shapes and sizes of pores within them, and they have these active sites which are demonstrated by the red dots, which are the locations where the actual reaction takes place. These materials are pretty robust, and that's why they have been employed in a lot of industrially relevant processes, right from petroleum refining to the processes leading up to the synthesis and manufacturing of plastics and pharmaceuticals. But these materials, however, suffer a limitation. When exposed to high temperature water, these materials deactivate, either because of the leaching of the active sites or because under some conditions their structures collapse. In either cases, your catalyst is now useless. And now, if you want to keep your chemical process going, you will have to replenish the catalyst, which would mean you're adding up to the cost of the process. My work involves preventing this deactivation by enhancing the hydrophobicity of these materials. The way we do this is by treating these materials with organic solvents. After treatment with organic solvents, we found that these organic solvents attach themselves to the surface of these materials, creating a thin layer which prevents the water from interacting with this material, kind of like a poncho or an umbrella for these materials. As you can see from the figure at the right corner, you can see that before the treatment, all the catalyst is finally suspended in water. But once it's treated with the organic solvent, it starts floating, which is because of its increased hydrophobicity. And it's not just that. When you expose this material to high temperature, as high as 600 degrees Fahrenheit, the hydrophobicity stays, which now means that you can use this hydrophobic catalyst even for high temperature reactions, which is a big thing, because most of the chemical processes take place at high temperature. So overall, I would say that we have demonstrated a very simple, inexpensive and efficient way to enhance the hydrophobicity of materials, which in turn increases the life of these catalysts. Thank you.